of the afternoon session is Hugo García-Compeán, who I guess we owe a small apology to. It's the schedule says Hugo Compeán without the Garcia. That's because everybody who knows him calls him Compeán, or mostly. All right, so he is from the Department of Physics at Cinvestav in Mexico City, and he will talk to us about realization of the classification of topological insulators and topological superconductors in terms of KK-theory. Hugo, go ahead.
Thank you, Mar, for the presentation, and I would like to thank the organizers for giving me the opportunity to give this talk. So, as Omar mentioned, the title of my talk is a realization of the classification of topological insulators and topological superconductors in terms of a KK theory. So, okay, let's start. As everybody knows, topological phases of matter is a subject, is a very important subject in different branches of theoretical physics, like condensed matter physics, high-energy physics, and mathematical physics, among others. And perhaps it's a prominent example of these topological phases of matter is the integral quantum Hall effect, in which the conductivity is discretized in integer multiples of certain quantity. So with the consideration of certain kind of symmetries, for instance, time inverse symmetry, particle Hall symmetry, and sublattice symmetries, we can have a plethora or more systems, more of these systems. We can have topological insulators and topological superconductors, which I will write down in this way. So these systems, these families or classes are classified by the 10-fold way classification in terms of K-theory, where the charge are C or C2. I mean integral charge or fractional charge. The classification is given by this table, in which we have 10 classes of systems given by these names in terms of two parameters. Well, one parameter, which is the dimension of the space-time, the spatial, in this case, the spatial dimension, which the topological systems lives. And in terms of the different symmetries, for instance, the family of type A, there are not symmetries in the system, and in 2 dimensions we have a topological charge, integral topological charge. This is precisely the integral quantum Hall effects in 2+1 dimensions. But there are many others given by this in this table and classified in principle by K-theory. So in this talk, I will focus in these 4 examples, but in order to be concrete, but we will consider any other of these systems. Okay, another ingredient of the important in my talk is the result of in 2010 Ryu and Takayanagi. They in order to reproduce this classification, they consider systems in string theory. In string theory, they use the so-called D-brane configurations. And in particular, they consider intersecting in D-branes with Dd-branes. So I hope that this will be clear in a few minutes. In general, this system of branes are not intersecting, but there will be some cases in which they are separated completely. They are not intersecting. Okay. In string theory, these D-branes, the charge of these D-branes are solitonic objects which are charged, and the charge is classified also by K-theory. This is one of the motivations by which Ryu and Takayanagi tried to relate topological insulators with string theory. The system describes, for instance, systems, la family A and A3, in terms of in the intersection of this kind of two D-branes, there is a field theory in L+1 dimensions. It's an effective field theory, which describes the associated topological insulator, as we will mention before later. These two models, in terms of D-branes in type 2 superstring theories, give rise to the classification of the complex classification is the complex classification of K-theory, and the remanent, the other 8 families, are classified by real K-theory. But in the context of string theory, the real K-theory, classified D-branes in type 1 superstring theory. Type 1 superstring theory is a theory in which the word sheets, the strings are not oriented. So there is a symmetry, orientifold symmetry, and this is the reason by which we have to consider OP planes. This is a figure taken by the Ryu and Takayanagi paper, which is given in this reference. So this is the D-brane, and this is the Dd-branes, two kinds of D-branes. So we have open string stretching between them, where we have one of the oscillation modes are fermions, which is a mass which depends on the distance between these two branes. Sorry. How I can, okay. So in each kind of D-branes, we have open strings which have modes, have zero massless modes corresponding to gauge fields, abelian gauge fields, if one is considering if we consider only one of these D-branes. You have many n, for instance, n parallel D-branes of this kind. We have UN non-abelian gauge group, and the connection, the gauge field will be Young-Mills fields, but it will be non-abelian, and similar for the other. Okay, in general, these branes, these two type of branes are intersecting. For instance, here, and the intersection, in the intersection, we will have the field theory describing the topological insulator. And these D-branes can be bending in an appropriate way, in such that we can give to the field theory in the intersection and a notion of boundary in order to have a bulk and a bulk where the theory has a gap. The gap is given by the mass of this fermion, and in the boundary we have a massless mode. The fermion is massless, so we have conducting modes in the boundary of this topological insulator. Okay, this is the complex case. In the real case, we have this system, and we have to introduce, in addition, one orientifold, one OP plane, and we have the mirror configuration with respect to the orientifold. I will try to give in detail this part, but if I have some time, I will mention these systems. Okay. This is also tables by in the Ryu and Takayanagi paper, and we have for the class A systems. For instance, we consider the D5 brane, which will be our D-brane, R equal to 5. And we have the possibility to have different D-branes, of Dd-branes. In the case of D5 brane, for the Dd-branes, so we have an the intersection will be 2 + 1 dimensions, and we will have the integral quantum Hall system in 2 + 1 dimensions. In the world volume, the effective theory is living in the intersection of these branes and these branes. So in this case, we have the Dd-brane is classified by K-theory, and in this case we will have that corresponds to a C-chart. Okay, this is very general, so I will be more specific. Can you see this part, or is it's only for me, or you?
We can see it.
Yeah, you can see it.
Okay. Okay, the brane configuration, more in detail, is given by our D-brane is the D5 brane. So we are considering this the class A models. We have a fixed D5 brane and another possibilities which can vary with our Dd-brane, which D is changing. We have three possibilities. We will consider D-branes also in order to have the 2+1 quantum Hall effect, integral quantum Hall effect. So where the D-brane of RK class has coordinates along these directions. In a string theory, we have nine dimensions. So some of these 9 dimensions are located. The D-brane are using these coordinates. Our Dd-branes is also a D-brane. So the coordinates, the D-branes are located in these coordinates. We have in common only the first 3 coordinates. So the intersection is, we have a space-time of 2+1 dimensions, where the field theory, the effective field theory is living. Okay, so the effective theory has a Lagrangian in 2+1 dimensions with a fermion, which coming by the open string modes, massive open string modes, which of a D-brane, of a open string stretching between these 2 kinds of D-branes. We have a gauge field, mu, which is a massless mode in this D-brane, and we have another gauge field, A tilde over the D-brane. So this is an internal field of the D-brane. So the interaction between this gauge field with the field theory, the intersecting the field theory, is given by the so-called Besu-Minot action in D-brane physics. The Besu-Minot action gives an interaction between the fields of the Ramond fields living in the D-brane and the gauge fields, the external gauge fields living in the other D-brane, the other kind of D-branes. So we have an interaction of this time. This is a topological interaction. And if we take the hypothesis, which C4 is A weight C3, then we can factorize, we can expand this part in the exponential and factorize this integration, this, of course, this Bohr volume of the D-brane with factorize. So we can obtain, we have an integration of this kind, which represents the charge, the Ramond charge of the D-brane. D-branes are charged on their, they have similarly as a charged particle can be coupled with a gauge field in electromagnetic gauge field. In D-brane physics, we have some charts on the D-branes are charged under Ramond charge, which couple to precisely the D-branes. So this is something like the flux of the, this is a measure of the charge of the D-brane. So this can be factorized, and the effective field theory in the intersection of I mentioned before, is given in 3 dimensions, in 2+1 dimension, as a Chern-Simons Lagrangian, abelian Chern-Simons Lagrangian. So in addition to this fermionic Lagrangian, we have the coupling of the fermions with the gauge field is given by this. Another way of obtaining this integration is integrate the fermions of the fermionic part. This is a path integral integration. So we will obtain again the Chern-Simons coupling. So this is a standard in 2+1 dimensions quantum Hall effect. And this represents we have only one of these Dd-branes. We will have only one unit of charge, or Ramond charge. But if you have many, a bunch and a stack of Dd-branes, we will of K of these spaces will have an integral charge, which is the level of the Chern-Simons theory, and which is precisely which gives produce an Hall conductivity, which I mentioned before as a multiple of an integral. This integral is given by the number of Dd-branes. Okay, well, this is regarding the work of Ryu and Takayanagi, intending to derive the K-theory classification. Well, in string theory, we have some fundamental objects, non-perturbative objects in string theory. This is the D-branes, in which open string endpoint can be attached. And the effective action of this D-brane is given by in the massless oscillation modes of this open string. One of them is the gauge field, as mentioned before, and other is the fermion having the Dirac Lagrangian. These D-branes are charged under Ramond field. Ramond fields are forms are multi-forms in 10 dimensions. So similarly, as punctual charge particles is charged under the electromagnetic field, these objects are charged and they are coupled to these Ramond fields. So these Ramond fields are P-forms in, so in principle, one will expect that the D-brane charts are classified by integral cohomology, but this is not true because the D-branes has a gauge field in the work volume. In the gauge fields is can be regarded as a gauge connection, which can be a connection in a principal or vector bundle. So it's more appropriate to classify these Ramond charts by K-theory instead of just cohomology. This is one physical argument. A few of this history of D-branes and K-theory. For instance, type 1 and type 2 superstrings are K-theory is necessary to define precisely the Ramond chart. This is given by Minasian and Moore. And in 1998, we then classified the Ramond chart in terms of K-theory. I will mention later some of these results. Okay, in 2000 and 2001, Periwal, Terashima, Akazawa, they give a classification of Ramond chart of D-branes in terms of not K-theory but K-homology. K-homology is the dual of K-theory. And soon later, Akazawa and the Japanese group, they generalize these results to considering Kasparov K-theory. I mean, K-theory contains K-theory and K-homology at the same time. So it seems natural, more natural to classify D-brane charts in terms of KK-theory. I will mention some peculiarities of this. Okay, in type 2 theories, the D-branes are classified, D-branes are obtained by solitons in systems with unstable D-branes, or pairs of brane anti-branes, or by a single unstable D-brane. An anti-brane is the same as a D-brane, but with the orientation change, with the other orientation. This system, brane anti-brane, has a tachyon, has an open string, which has a tachyon. So the system is unstable. So this can decay into to form precisely a D-brane of lower dimensions. For instance, we can start we can start considering an system of a D-brane and a anti-D-brane. So these systems is unstable and can decay into a D7 brane. So we can construct or classify all lower dimensional D-branes in terms of an unstable system in 9 dimensions, for instance. So, and the K groups, for instance, you have a D7 brane, D is equal to 7. So we will have DR 9 minus 7, KR2. This is C, and this is precisely this classification. So we can obtain this recursive method. You can obtain all lower, starting by an unstable system in 9 dimensions. We can obtain the lower dimensional systems by D-brane decay, by decay of this unstable system. So we can also start not in precisely in 9 dimensions, but we can start in another dimension, in another dimension. This is precisely the cube. For instance, we can start in a defined brane Q equal to 5. So we can construct the lower dimensions, D-branes, starting by an unstable system in 5 dimensions, and similarly for the other dimensions. Okay, I mentioned that we have a tachyon. The tachyon is a field which is transverse to the codimension, is in the codimension of Q minus D. I mean, is in the transverse directions to the Dd-brane inside the DQ brane. So the tachyon is a function given by the coordinates transverse to the Dd-brane in the DQ brane. Here Q is equal to 9. So this is the multiplication of these coordinates by the Dirac gamma matrices in these transverse dimensions. And this way of constructing the lower dimensional D-branes is a physical version of the so-called Atiyah-Shapiro construction in the mathematical literature. So we can construct all lower dimensional D-branes starting from a higher, the highest system, the highest possible system, which is unstable. Okay. Something similar can be done for starting by the lower dimensional system and construct all D-branes of higher dimensions, starting by the unstable system in the lower dimensional. For instance, we can consider a system of non-BPS D minus one brane, the so-called systems of instantons and anti-instantons systems. This system is unstable and has a tachyon. So we have this is the unstable system. We can, in this case, the tachyon is given in the transverse dimensions for the unstable D-brane. Is different from the other because in this case, in the case of K-theory, the tachyon runs, the index A runs over the transverse dimension of the D-brane, but is inside the unstable 9 brane. In this case, is transverse to the unstable system. So it's possible to construct to perform such a construction, and in this case we will have not K-theory but K-homology classification. So in K-homology we can obtain the higher dimensional D-branes in terms of an unstable system in the lowest dimensional possible lowest dimensional system. Okay, well, I don't give any detail of this, but there is a very interesting theory of K-homology in terms of triplets. So these two ways of it's also this construction also gives some physical view of a Shapiro construction, but in the inverse direction. In the case of KK theory, we consider a Dd-brane, which is located in these coordinates. This is proposed by Akazawa, Sugimoto, and Terashima, the Japanese group, in this year. So they consider a D-brane, Dd-brane, which is in part inside the unstable D-brane, unstable Q-brane, and in part in the transverse direction. So the part of this D-brane is given in the first part is classified by K theory, and the other is classified by K-homology. So we can have both systems in the same packet. Okay, so the tachyonic configuration is given by a contribution of both modes, both tachyons. One stretching to the S part, the S coordinates inside the unstable DQ brane, and the other the rest in the transverse directions. Part of theory is a bifunctors. So we have two spaces. Here are two C-star algebras. In the case of abelian C-star algebras, they leads to the ordinary KK theory, topological KK theory, where X is a topological space, X and Y are topological space. But in general, this can be generalized by non-commutative algebras. But in our case, they will be abelian. I mean, they are only topological spaces. If we take X a point, just a point, this Kasparov theory leads to the ordinary K theory, the description of in terms of K theory, and if Y is a point, we will have another description in terms of K-homology. The theory of the Kasparov K theory is very rich and very complicated, and is given in terms of cons or Kasparov triplets, which has also a physical interpretation. Thus, I skip here. Okay, so in the context of type 2B, of type 2A theory, the proposal of Akazawa is having an Dd-brane in these coordinates. Let me check the time. Okay. So we have a Dd-brane, which is in part inside the unstable Dd-brane. This is in red, and we have another part of the Dd-brane in the transverse space. X is the space transverse to the Dd-brane. This in the whole space in 9+1 dimensions in theory, and this Y is the space, the transverse space to the Dd-brane, the part of the Dd-brane inside the DQ brane is the is the codimension Q minus D. Well, Q minus S. So X is given by this space, R to D. Actually, we can take we will consider the reduced K theory, and these non-compact spaces will be substituted by the spheres with these dimensions. So this is the dimension of this X space, and this is Y. This is Y. This is 9 minus Q minus plus S. So the proposal as the Japanese group is that these D-branes Dd-branes are classified by these groups, by KK group, and using the isomorphism of the theory is given by the K theory of, this is the complex K theory, the complex K theory. Okay, there is also a proposal of Kasparov KK theory, but for type 1 superstring theory, which is a theory with orientifolds. And the orientifolds has a symmetry of projections. This removes the orientation of the open string. So we have worksheets, unoriented worksheets. So in this case, the K theory, the relevant K theory is a KKO, is an orthogonal KK, is a real KK theory. And the K proposal KK theory is given by this. I will have no time to introduce the part of orientifolds, but let me go back to the case of complex KK theory. Okay, we consider the first example of the class A in topological insulators, topological superconductors systems. Consider the intersection of these Dr and D-branes. This is precisely the three-dimensional topological defect. This is the effective theory of is living in 2+1 dimensions. We have the integral quantum Hall effect here. This is done by considering a Dd-brane of dimension 5, where the intersection is given in this precisely. This is the space-time where it's living the theory in the topological insulator, perhaps with a boundary in one of these directions. Okay, sorry. Okay, but in addition to the Ryu and Takayanagi proposal, we have in order to connect both description, we introduce a D7 unstable D-brane, unstable brane, stretching with coordinates along these directions. So, and in order to describe this by KK theory, we have this D5 obtained by the decay of this unstable system. given rise to the K-theory charts. And in order to introduce K-homology, we have a lower dimensional unstable brane, which can give rise to this D5 in the transverse direction. So these two unstable branes are important in order to have KK theory, KK functor. Okay, we will go back here. So this if X is a point, so we will have the case of a K theory, but this is a point precisely when D is equal to Q minus S. This is X, this is just, this is exponent is 0. So we have X is a point. So we have the case of ordinary K theory. This is precisely the work of Ryu and Takayanagi. So in this case, D is equal to 5 and Q is equal to 7, S equal to 2. And the white, this index, the exponent is 4. So in this case, we recover precisely the classification of this integral quantum Hall effect. This is the K theory of R4 is equal to C. This is the integral chart of the usual integral quantum Hall effect. So we have the ordinary case of Ryu and Takayanagi. But in this system, we can more possibilities. In this case, the D-brane, the D5 brane is completely inside the unstable D7 brane. This is so we have the limit, which is described by K theory. But we can consider the case when the D-brane is completely transversal to the unstable DQ brane. But in this case, Q is equal to 3. This is another case. So we have a D3 brane, unstable D3 brane in these coordinates, in this 3 plus 1 dimensions. Okay, so so in this case we have S in order that the D-brane is outside completely of the DQ brane. So S has to be 0, Q is equal to 3. So so the D6, the transverse D-brane, the transverse D5 brane is in this, has to be in these directions. Okay, so we obtain the K, the system is described by the K-homology. Sorry, this is described by the K-homology. And this is in K-homology. I didn't mention that this is described by a so-called matrix K theory, which are systems has Lagrangians or Hamiltonians, which is where the coordinates are matrices. But we have the general case, in which part of the D5 is inside the unstable D-brane, and part is outside this D-brane. So if we take S equal to 0 and Q equal to 3, so we can the case when X and Y are not trivial, they are none of them are points. So we have X, we have R2 and Y R6. This is precisely the space X. It's the transverse space to the D7 brane, and Y is the transverse space to the D3 unstable brane. So, but this is a general situation, a general case where part of the D-brane is along the DQ brane, the unstable DQ brane, and the other is transverse to this, is outside of this D-brane. So we have a situation which is classified by non-trivially by KK theory, a complex KK theory. So we can compute with these numbers, we can compute the group, which is precisely the same result, is the integral which appears in the integral quantum Hall effect. But the difference is that now is obtained or classified by KK theory. Okay. Okay. I know I have not much time, so I would like to mention that something similar. This is the case for a complex K theory, and there are similar. The other systems can be classified by KK real K theory. So I don't want to give the details because this is the short version of my talk, giving the details of this construction, but it's something similar can be done for the real case. So the real case requires from orientifold planes. An orientifold is a plane in p dimensions. It's a plane in p+1 dimensions. This orientifold is a plane with these coordinates. And in the transverse coordinates, we have the application of some groups. For instance, the change of the orientation of the worksheet, the orientation of the open string is this is a parity symmetry in the transverse dimension, in the 9 minus p dimension, and J is a fermionic number generator. So the transverse dimension to the DP or P plane are acted by some symmetries, and this in particular omega, if right, is a symmetry which gives is the so-called orientifold projection, which changes the theory from complex to real. So there are two types of orientifold planes according to the possibilities of the action of the twofold action of the orientifold. One of them is the ordinary orthogonal groups. In this case, is the symplectic, is the quaternionic planes. So the ordinary SO 32 theory is with using planes P equal to 9 with negative Ramond charge. And this gives rise to the type 1 theory in string theory, which is a supersymmetric theory. But if you take the symplectic case, we have orientifolds, 9 orientifolds with positive charge. And in this case, the theory is not supersymmetric. And this is called exotic plane, exotic orientifolds. So there is, in the context of K-theory and string theory, there is also a classification for these orientifolds, for D-branes inside these orientifolds. And there are some results by Witten and by Hugo, where we have D-branes inside orientifold planes. So once again, KK theory can be used here, and we have different situations in which we have our Dd-brane inside an orientifold plane. I mean, D is lower than P, and in terms that OP plane is inside this DQ-brane. This is a possibility and possible scenario, or we have where the O plane and DQ-brane are interchanged. So we have our Dd-branes inside our unstable DQ-brane, and this is inside an orientifold plane. So the proposal, for instance, this is the more important for us, the more important case for us, where the orientifold is the highest dimension. So the proposal is that we give in one paper in 2009 that the relevant KK theory classifying Dd-branes with this in this configuration is given by this group in terms of real KK theory. This is general for any P, for any Q, and for any D, and for any number of coordinates that the Dd-brane is inside the unstable DQ-brane or in the transverse part of the unstable DQ-brane. Okay, this is our proposal. So we use this proposal in order to give to classify using KK real theory of some topological insulators, topological superconductor systems. For instance, the the class C. Sorry, C is in two dimensions. Is classified by C also in this classification in 2 dimensions C, and the other in 1 dimension is D, and we have the system D, and in 4 dimensions the same system C is given, it has a fractional chart. So, well, using this prescription, for K-theory, we once again we show that we can for some in some limit we can recover the result by Ryu and Takayanagi, but we give another examples, additional examples. Perhaps one important thing that I would like to mention is that is the following. For instance, the case of when our Dd-brane is a D-brane, this is classified by, this is given by the D system, and it has a fractional chart. But this requires of exotic orientifolds with positive sign, positive charge. This gives the D system. In other words, is precisely this. So this requires of exotic the exotic orientifolds. In this same paper, in this paper, we also gives the prescription for groups. The proposal is a proposal for the classification of Dd-branes inside unstable D-branes with exotic orientifolds, and this is in terms of quaternionic K-theory. And our proposal is given is this, in the case where we have a part of the Dd-brane in the unstable D-brane and part in the transverse coordinates. So for this system, we compute we recover the result by Ryu and Takayanagi using precisely this prescription. So the final result is precisely the fractional charge that one expects here. So as mentioned before, this is a paper in progress, a work in progress. So it's not complete. Our list we shall to obtain following working to obtain the rest of the. So our conclusions are the following. We review the Ryu and Takayanagi proposal regarding the tenfold way of classification of topological insulators, topological superconductor systems in terms of D-brane configurations. On the other hand, we review also our proposal of describing the D-brane in terms of KK theory, complex KK theory and real KK theory, and even quaternionic KK theory. So in particular for the real K theory, this is our proposal. And we match both proposal into a description of these systems. So we hope, we expect to, we hope to following working in this subject. And please, all your critics and questions are welcome. Thank you very much for your attention. I'm sorry by the extra time I take.
All right, let's thank Hugo for the talk, and we may have time for one quick question, but we are a little bit over time, so not more than one question. Does anybody want to ask? I saw a hand go.